And the recording has started for the Bridge Day. We're so excited to have everybody here. If you are just joining, please do not forget to please add your school name so that when we do open up the breakout rooms, you are assigned to the correct room. We are excited to start our Bridge Day, and we have Mr. Edgar Martinez, who's going to be starting our day with the introduction to bridges. And I'm actually going to just remind everybody to please, last housekeeping, remember to please change your profile name so we can recognize you and your school. Please, we love student engagement and student participation. Do not hesitate to type in chat if you have a question or comment, but I'm going to stop speaking because our presenter is here and ready to roll so we can get this day underway. And Mr. Edgar Martinez, if you want to take it away for our bridge intro for our Bridge Day. Oh, you're on mute, Edgar. Still on mute. We cannot hear you, Edgar.
I'm locked out.
There we go.
Can you hear me now?
Now I can hear you. Yes.
Can you see my screen?
We can see your screen. And now we see the presentation. Now we see the presentation. Right. Yep.
Good morning, everybody. My name is Edgar Martinez. I'm one of the engineering presenters for Engineering Tomorrow. I'd like to start on behalf of the Engineering Tomorrow team to welcome you to today's presentation on bridges. It's exciting for me to be here, especially when I get to work with ET to talk to you a little bit about my passion, right? I am currently a principal in a high school, an assistant principal actually, but before I started doing this, I worked as a civil engineer. I am a graduate of Columbia University, and I went through their engineering program there. So if anybody's interested in any questions, put it on the chat. Our discussion today is going to be focused on bridges. So I'd like you to take maybe a little bit of time to consider what life would be like without bridges, right? You may have crossed a whole bunch of them this morning and not even thought about it, right? On the way to school, on your walk to school, right? And just think about how important they keep us connected, right, in our communities. So without bridges, things would be a lot different, right? Just think about travel times, just basic travel times, how much that would change. And so that's what we're going to discuss today, right? So the goal today is to design and create. At some point, you're going to be able to go on to your breakout groups and actually work with the material that Engineering Tomorrow provided so that you can design a bridge of your own. So let's talk a little bit about bridges, right? That's what we're here for. So first of all, I'd like to thank the breakout development team. There was a group of people that worked on putting together all of the amazing slides and all of the kits that you received today. From Joanna Corell, who is a mechanical engineer. She currently is teaching at a school. I think she may be retired, but she graduated from Georgia Institute of Technology. And then we also have a couple of graduates that worked in different engineering disciplines that also contributed to this breakout. So let's get started a little bit. So definition of a bridge. A bridge is a structure that is built to span physical obstacles, right? So you can see here 3 different types of bridges. These are all bridges and they all do the same. They are spanning over something. They got to get you over something, right? That's what bridges do. But I'd like you to take note, right, that they all look different, right? They have different materials. They have different designs, right? And that comes to the reason for that is because there's a lot of things that go into making a bridge, from cost, right, to what material is available, to what does it need to look like, right? Aesthetic, how does it look? For everyone who's on this call, if you're interested in working in bridges, just know that in America right now, in the United States, we have over 617,000 bridges. A lot of them are new. Some of them need a lot of work, right? So if you're planning on becoming a civil engineer or even a mechanical engineer who wants to work on the devices that control some of these bridges, right? Just know that there will always be a job for you, right? So moving on, right? Today's keynote speaker will be Avery Bang. You will meet her later today. She is the CEO and owner of a not-for-profit organization called Bridges to Prosperity. And what they do is they build bridges in rural areas. Why are bridges so important, right? Because again, they offer access to schools and markets, right? And doctors, right? So that's really, really important, right? If you didn't know, there's over 1 billion people in the world who don't have safe year-round access to education, healthcare, and markets. And the reason that is because some of them, they are so isolated, they don't have bridges, right? So Ms. Bang will talk a little bit more about what she does and where she does this a little bit later. But just know that bridges are important because they allow students to get to school for education, right? They allow people who need healthcare to reach their doctors, right? And even if you need food, right, markets. So they connect people, and that's what's really, really important about bridges. All right, so let's talk about bridges a little bit. Here I have 4 different types of bridges, right? And even though these bridges look different, right? Notice that there's 4 types of bridges. So the first type that we see here is part of a integrated transportation system. It's a fancy word of saying a bridge has many uses, right? So in this case, we have a train, we have cars, right? But some integrated transportation systems are like cars and people, right? Cars and bikes, so that works, right? Here in New York City, I can think of the Brooklyn Bridge, right? We have bike lane, people walking over it, right? And we also have cars traveling over it. The Manhattan Bridge here in New York has a train and cars, right? So these are all integrated together, right? Then you have different types of bridges that can traverse really strange obstacles, right? Obstacles. And these obstacles sometimes will determine what kind of design you have. So this floating bridge in Washington, right? That's a special design, right? So thinking of the obstacle that it has to get over, right? We have mobile origami bridges that allow people to get in and out of areas that have been devastated by natural disasters like earthquakes or even hurricanes, right? And then, of course, we have really nice bridges. This example right here in the bottom right corner is a cable stay design, right? And it adds to the beauty, right? Bridges can literally transform the landscape of a city, right? So something to think about as you're designing your bridges, right? And even though these bridges all look a little different, right? They have the same fundamental design, right? They use the same fundamentals when you're designing them. So we talk about forces, we talk about compression, right? Compression is a force that will squeeze together. So if you can maybe look a little bit on the screen where I'm speaking, right? Compression is the force that'll squeeze. So I don't know if you can see, I have a long, slender spaghetti and I'm squeezing it, right? And as I squeeze it, notice that it's bending. That's the compressive force, right? So when we're squeezing something, we call that compression. When I'm pulling it apart, right? When I'm pulling it apart and it's hard to pull apart, that's called tension, right? Balancing those forces are really important. And that's what goes into designing a bridge, right? So I'm going to share a different screen with you, okay? Because on my other screen, what I have is actually a bridge design that I want to show you. So let me just, give me a second while I pop this open. New share, so let me go here. Give me 1 second, thank you for your patience, right? Screen 2, and just let me know if you can see the screen that I'm sharing. Let me do it now. So you should see a bridge on your screen, is that right? Give me a thumbs up. Can you see that bridge on there? Yeah. Okay, so here we have an actual a design bridge, where I'm using Bridge Designer, which is a program that you could download on the web. And here what we have is just a basic truss bridge. And notice that each of these pieces here, what we're going to call our members, are different materials, right? So in this case, these are all carbon steel bars, right? And I'm going to load test it, right? We're talking about tension and compression, right? So when I'm going to load test it, what you're going to see is it's going to undergo some loading. So you can immediately see that there's going to be a truck passing over it. And notice that all the members are changing colors. By the way, red in this case is for compression, blue is tension, right? So what I want you to notice is that a lot of these members are stressed differently, and knowing which members are undergoing tension, which members are undergoing compression is really important when you start to design your bridge. So I'm going to get out of this because I do want to show you something, right? So I'm going to go back to the drawing board. Each of these members are the same, but what would happen if I changed one of these members, right? So I'm going to change this solid bar. It's carbon steel. This is member 9. If you look here, right? I'm going to change that and I'm going to make it something thinner. I'm going to make it something like 120 by 120. That's all I'm doing is changing the dimension, the size. So when I do that and I load test it, I want you to notice what happens. So let me load test that again. And you'll see now that one of the members in there looks a little bit more stressed than the others, right? The bridge is still serviceable, right? That means that it still works. If you are a driver on that truck, you probably don't want to be on that bridge because it will probably move a lot more than it usually does, right? But notice that this member is stressed more than the other ones, right? So understanding how the forces move through that bridge is really, really important. What I'm going to do now is I'm going to go back to the drawing board. right? And I'm going to change it again because I do want to show a failure, right? So I'm going to go to the drawing board, and now what I'm going to make, instead of making it 120 by 120, I'm going to make it something like 100 by 100, right? When I do that, I've changed it. I'm going to load test it, right? And you'll see that's going to be, the red is going to get dark, and it will probably fail here. There it goes, right? So you can see that it fails, right? So it's really, really important to understand the interplay between tension and compression when you're designing your bridges today, right? Think about which pieces that you are going to put together are being squeezed together. Think about which pieces are being pulled apart when you start load testing. So I'm going to go back to the presentation. If you have any questions, of course, feel free to put them in the chat as we go along. Okay, so are we back on? Yep, we're back on the screen with the presentation. So moving forward here, we spoke a little bit about compression and tension. I think that you were able to see something. So today, when you start to design your bridge, do a little research. There's a lot of different bridge design options. You could do something from a beam bridge, right? Maybe you want to try your hand at a suspension bridge. These are a little bit more challenging, right? Most of you will probably be working on a truss bridge, right? Notice the shape of triangles, right? And understanding, again, the interplay between the forces is really, really, really important, okay? A timeline of bridges I have here just to speak a little bit about how bridges have changed over time, right? Simple bridges in the prehistoric time, which is basically like trees that fell over so people could cross over. With the advent of new materials and stuff, right? We had arc bridges that you saw earlier on, or even stone bridges. Stone bridges like the one in this top right corner, they look really nice, right? Stone is a very strong material in compression, but notice that it's really heavy. So because the material is so heavy, it's really hard to use it to traverse really long spans. So something had to change. We had the advent of iron, right? Iron is malleable. It means that you can form it, you can cast it, right? But iron is very brittle, right? So even though iron will give us access to make these types of bridges in the bottom left corner, which are like these open truss bridges, right? The material has its drawbacks, right? It is brittle. Brittle is like, it can crack easy, right? Which is a problem. It's also susceptible to the elements, right? Salt water will affect it, cause it to rust, right? And I don't think that you would want to cross a rusty bridge. So what happens? What do we think about that? Then we had the advent of stainless steel, right? Steel and stainless steel, right? Stainless steel, when I think about bridges, stainless that have stainless steel in them, or even steel, they have chromium, but they also have like carbon components in them, and that makes them less susceptible to the environment, right? Stainless steel will not rust. The issue with things like that is that they get costly, right? They get costly. And so there's an interplay between what do I need to do, the function, right? How much will it cost? And do we have the money for it, right? Do we have the money? Do we have the material for it? So to recap, all right, bridge designs depend on function, location, material, and budget. You've seen that with all the different bridges we saw today. Bridges work by balancing compression and tension. I think that we saw that with the bridge designer. And then bridges are designed and built using the engineering design process. We'll talk about that in a little bit, what that is. Today, your challenge will be to design, build, test the bridge to maximize load. The bridge that you're going to build today, you want to make sure that it can take the most load that it can. So that's going to be interesting. How do you get that to happen? And you're going to do that practicing the engineering design process. So you're going to do iterations. You're going to do this a couple of times just to make sure that your bridge is working at the capacity that you hope it has when you design it. So here's a little bit of what the engineering design process looks like, right? You do a little learning. So you're probably going to start with some research, look up different types of bridges, right? Think about why different bridges look the way they are. So that's going to be part of your task. Then you're going to design. Dr. Wilson, my college professor in my construction management class, he say all the time, proper prior planning prevents poor performance. So that's a lot of alliteration. I'll say that again. Proper prior planning prevents poor performance. When you are designing, that's when you really want to make all the changes that you need to, right? Because once you start building it, right? Think about it. Once you start building it, it's more challenging to make changes then. All right. So design your bridge, think about what it's going to be, and then start building it, right? Think about what material you're going to use, right? Build it. What are you going to use for your connections? When you load it, which members are going to be taking tension? Which members are going to be taking compression? Test it, right? When you test the bridge, just like I showed you on the bridge designer, when you test the bridge, you're going to see that there's going to be a lot of your bridge is going to behave in different ways. Think about how to reinforce that, right? And then if you have time, go back and redo it, okay? There are mathematical equations when we talk about bridge design, right? So this is the fundamental equation. It's actually Hooke's law, right? So for those of you that are interested, right, force is equal to the stiffness of the material, this times the deflection, if you will, right? Whether it elongates or gets compressed. But this equation, this basic equation that you see on the left is actually when you are designing bridges gets combined over here, right? And what this last equation basically says is that the deflection of a bridge is proportional to the force and the length cubed, right? So even with the spaghetti example that I showed you, right? And I can show you this immediately here, right? If I have a really long piece, it's easier to bend, right? It's easier to bend. There's a lot of deflection in it, right? Whereas opposed to if I had a really short piece, right? It's harder to bend, right? So we call that unbraced length, designing these structures, right? So think about it like that, right? And of course, this deflection equation will also contain things like the material, which is symbolized by E, right? And also the shape of the material, right? Whether it's an I-beam, right? Whether you're using a rectangular piece, right? Whether you're using a round piece, right? That's all incorporated in that. So when you go through your workbook, maybe sit down and take a look at these equations with a little bit more scrutiny, okay? Moving forward, right, we spoke a little bit about different designs that you can look at, right? Here are some examples, which of course you'll be able to find in your workbook, right? And what's important to know is that shape matter, right? The shape will matter. And again, we know that because in the equation for deflection, you see the moment, the inertia is here, right? The inertia is related to the shape. So think about what kind of shape you're going to use, okay? Lab overview. Let's talk a little bit about what you're going to do, right? So what is the problem? You're going to build a bridge today, right? What do you want it to do? You want to maximize the load, but you also want to do it for, you want it to be cost effective, right? Do some research. What design could you use? Should I build a truss bridge? Should I go for a cable stayed bridge? Do I have the material to do that, right? Design your solution, which we spoke about, right? Draw your diagram, think about what it's going to look like, then build your first prototype and then test it. See how the bridge reacts, go back and make some changes and do that a couple of times until you are content with your design, okay? A couple of design constraints, right? Your bridge has to be 12 inches. So I'm going to slow down now so you write this down, right? Your bridge should be 12 inches or more in length, okay? The bridge must also be 3 inches or less in width. So the deck should be 3 inches or less in width, right? The bridge can be as tall as you need, and you have to use materials found at home, in your school, or in your ET toolkit. Testing restrictions. In order for you to test it, you're going to need 2 chairs. Okay, you got to set those chairs 11 inches apart, which makes sense because your bridge is going to be 12 inches, so it's going to be longer than that. Right, place your bridge on the chairs or table. Right, make sure that the end of the bridge extends about 1 inch beyond the chairs or tables, and then you're going to test. You're going to test the strength of your bridge. Okay, so I do have a video of one of our interns testing their bridge. You take a look. Give me a second. I'll play that. Stop the video there because as you can see, the bridge is already starting to deflect, right? And this is the point where it's really important for you to take notes when you design your bridge, right? See where it's behaving, right? This is a good point to think about where in your bridge you want to strengthen and where you can take some material out, right? Because you don't want to over-design a member either. You don't want to over-design a piece of your bridge, right? So think about which pieces are really strong, which pieces are really weak in the capacity that they need to be strong or weak, right? And also listen to it, right? One of the things that I know about engineers is that structures will make noises, right? They speak to you, So listen to the bridge. You're going to hear some cracking, right? Depending on what material you use. If it's glue, you're going to hear the glue kind of pulling apart. Listen to it, right? Think about what is weak, what is not so weak, right? So to analyze the results, we do ask you to cost your bridge, right? Depending on which materials you use in there, there is a cost associated with it, right? Ideally, what you want to do if you were part of a bid is you want to have the best bridge, the best design, but you also want it to be cost efficient. So when you're going through your bridge and you've decided that that's going to be your final design, give it a cost, right? What you ideally would want is a really, really strong bridge at a really, really cost-effective price point, right? And, you know, that is the challenge that you're going to be working on today. So if you have any questions, now is a good time to ask. Otherwise, I will let you go and start doing some research before you create your designs. Any questions?
This is your opportunity to ask Mr. Martinez any questions. It can be about the bridge or about his background. Don't be shy. You can type in chat or shout out before we open up the breakout rooms and you guys get right to building. No questions?
Oh, we do. We have Academy of Mount St. Ursula asked about floating bridges. What is specific are they asking about floating bridges? What type of material, right? So again, a floating bridge, the construction on a floating bridge is really complex, right? You would need a very special contractor to do that, but you would also need a special set of engineers, right? Because there's going to be so many complexities. When designing over a floating bridge, you have to consider not only the amount of traffic, you have to, the amount of traffic that goes in that waterway, right? You're not going to build a floating bridge on a piece of waterway that is used by boats, right, to come in and out. You also have to consider the currents, right? Some things that people don't consider when you're designing and you're putting up a bid, you also have to consider the environmental effects that a floating bridge would have, right? They are costly. That is kind of basically the rule, but they're also, you know, if there is no other option, that is usually the bridge that you're going to have to build in that application. So if you want to ask specific questions about that floating bridge, please feel to put it in the chat. Any other questions?
I think they're all excited to get building.
Okay.
I don't know how much research is going to happen.
Okay.
All right.
All right. Thank you, everybody. Thank you for allowing me to come into your classroom and speak to you a little bit about bridges today. I hope that you have a good design day.
I want to say thank you to Edgar for leading such a great and engaging introduction to bridges. I'm going to pause the recording to go over some housekeeping. Welcome back, everybody, from your breakout rooms. Right now, this is going to be our Q&A with our amazing college mentors who are here to answer any of your questions that you have. And this is your opportunity. So we love student engagement. I see that you guys are busy building, but if you have a question, please feel free to type in chat. And I'm going to stop speaking so that they can introduce themselves. We have Sarah and Emily here. Some of you may have met Emily in a breakout room, but they're here to officially welcome you. And I'm going to start off with Sarah to open up the Q&A. But again, this is your session. Your engagement is encouraged, and we want to hear questions from you. So please feel free to type your questions in chat. And Sarah, if you want to take it away.
Yeah, thank you, Monica. Hi, guys. Happy Wednesday morning. Hope you guys are having fun building your bridges. So first off, my name is Sarah. I'm a junior at MIT, and I'm just going to basically go through a few quick slides about my background. Emily's going to do the same thing, so you guys have a better idea of what we do, and then you can ask some questions depending on what you're interested in. And obviously, if you need anything for your Bridges lab, feel free to interrupt at any moment. This. Can everyone see this? Yes? All right, cool. All right, so quick intro. My name is Sarah. I'm a junior at MIT, majoring in biological engineering and management. If any of you have watched like Spider-Man, the last one, yes, that's the school that they mentioned in the movie. I've gotten a lot of questions about that recently. As for Engineering Tomorrow, I've been with them for a few years, and right now my main interests in engineering deal with treating complex diseases like cancer and diabetes with cutting-edge techniques like regenerative medicine, and gene therapy. You guys probably heard those words thrown around, and I can explain more later. As for what I actually do on a daily basis, I made you guys a little timeline because it's kind of confusing. I've been doing research for a really long time. I've been doing research since I was a freshman in high school. And that was when I became really passionate about leveraging biological mechanisms to our advantage to combat some of the world's biggest problems. So climate change, harmful algal blooms, and antibiotic resistance. And then when I moved to MIT, I got into a more academic lab. I started to investigate how bacteria talk to one another to exchange their genetic material and get traits that they didn't have before. So imagine like you shook someone's hand and you got one of their traits. That's kind of what bacteria are able to do. Then last summer, I did an internship at CRISPR Therapeutics. It's a biotech company in Boston, Massachusetts. And they basically focus on using stem cells, regenerative medicine to target cancer and diabetes. And now, during the fall, I've kind of shifted a little bit. And now I'm working at this investing firm called Agnes Ventures, where I'm using my engineering background to actually start healthcare companies and try and address all those problems that I was addressing through research back in the day. So kind of diverse experiences, and you guys can feel free to ask about any of them if you're interested. And then some quick pictures. I was in the same place as you guys. Research-wise, I started doing research in my basement with this really sketchy setup of plastic bins that I bought from Target and duct tape. And then eventually I leveled up to actually doing research in the back of my school's biology classroom because my school got really suspicious of like all of this stuff that I was doing in my basement. And then when I moved to MIT, I started working at this very nice building, the biology building, and then some pictures of me at CRISPR. That was a huge upgrade. So you can see I've kind of gone from being just a curious high schooler to being able to explore all of my interests in a more defined and much better funded way. So if you guys have any questions about that, happy to answer them, but I'll pass it to Emily for now.
Yeah, so hi everybody. I'm going to introduce myself and start sharing some slides as well. So just give me a second. Alrighty, so let me tell you all about me. So hi everybody, my name is Emily. I'm a senior at Columbia University studying mechanical engineering with a minor in earth and environmental engineering. So I'll talk a little bit about my interests and things like that, but particularly I'm interested in sustainable development in terms of like machinery and devices that we have, roller coasters. So if y'all have ever been to a theme park, so like Disneyland, Six Flags, things like that, mechanical engineers were behind those designs and attractions, and then also interested in product design. So for example, a professor that I had last semester helped invent the Swiffer. So if you have a Swiffer at your home, things like that, interesting to me, products for the consumer. Alrighty, so I stole Sarah's slide, but I've made it a little bit more custom to me. So kind of what my journey has been like. So in high school, I was again interested in electric vehicles and kind of like renewable energy. So I made an electric vehicle similar to what Engineering Tomorrow has, but instead of just with a solar panel and a motor, I instead use a reversed fuel cell. Yeah, no worries. We love to hear the engagement of the classes. But anyway, so for the reverse fuel cell, essentially what's happening is it takes water, and then in the process of heating up, the release of the hydrogen and atom bonds, when they split, it creates energy, and that energy stored lets the car move. So that's something that I was really interested in high school, and I created a model of that and like a small scale of that for one of my senior projects. And I took some engineering college classes, so in dual enrollment, so that I was able to get some credit and make sure that engineering was something that I really wanted to pursue. Between 2019 and 2020, so from when I first started college up to this point, I have participated in a program with NASA. So if y'all have any interest in aerospace, we can definitely talk about that. I've also interned with Con Ed, which is a really big energy provider in New York. So that is something that I learned, and kind of learning about energy conservation technologies, the limitations of them, and how we can hope to develop them in the futures. Last summer, I did research at Columbia. So I did 3D modeling of rat reproductive systems to understand how the tissues are have different characteristics at different stages of pregnancy to try to reduce complications in human births and things of that nature. And this year, I am a senior, so I'm doing a lot of more like senior design projects, but I will be doing my master's at Columbia next year. So just kind of also focusing on that because I'm starting to take some of those classes so that I can graduate with my bachelor's and master's in 5 years instead of a typical 6. So I also have some questions, not as good because these are literally from like lab reports and things like that I just like took. So in this first right-hand corner, it was a solar panel tracker. So essentially when we think about solar panels, we think of them stationary on top of roofs and things like that. But because of that, they're not very efficient. So thinking about how can we make them more efficient? Well, if solar panels moved with the sun, they'd be able to collect a lot more energy. So with that, we created this solar panel that had a light sensor on it. So basically every like 5 minutes or so, it would do an iteration and go through a whole cycle. And from that, it would communicate, the sensors would communicate with the motors to see where the brightest light source was coming from. And it would go back to that point, stay there, and then redo it. We also did some testing with like modulus and like strain and stress and things like that. For another experiment, we just were using sensors to kind of get into the understanding how they work and understanding how, like when you blow on a hot bowl of soup or a hot bowl of, or like a hot chocolate or something like that, like why does that actually work? Things like that. And then this was the car, the hydrolysis car that I worked on in high school. And then I also just put in some like other group things that I've done in college, just to show that like, even though you're an engineer, you don't have to do engineering all the time. So I did Glee in high school and in college in my first year. We performed at like the botanical gardens. And then this right picture, I coached track and field for a middle school. So that was my team last season. So a lot of fun things that you can do as an engineer. It doesn't always have to be engineering. But yeah, that's my slides. And we can open it up to questions now.
I know that they're busy in their classrooms. We can see some of their classrooms. I see they have some bridge building still going on. But do we have some questions for our mentors? You can type them in chat, and if the audio is okay, you guys can unmute and pop off your microphone and ask a question.
Yeah, you guys can ask us about anything about our college experiences. If you guys are juniors, seniors, kind of looking to apply, if you're looking for, more targeted advice, if you're kind of asking what's the difference between majors, we're happy to talk about all of that. Emily, I think this is a question for you in the chat.
Yeah, sounds good. What was the name of the space program you went to? So the program that I did was called L Space, so L''space. So it is for college students, but once you get into college, you can do it at any level. You can be a first year, you can be a senior, but they also do some high school programs. So if aerospace is something that you're interested in, you might want to look into those things. But I see that one of the schools has its hand raised. Do you all want to?
Oh, sorry. I think someone's talking, but you guys are muted.
What math classes do you guys take in college?
What math classes do we take in college? Sorry, did I hear that right? Yeah.
Yeah,
Okay. Okay. Yeah. There's probably different answers for both Emily and I, but I think for basic stuff in freshman year, before you kind of start your major, you take usually 2 semesters of calculus. If you're an engineer, probably 3 semesters of calculus. And you take 2 semesters of physics usually. I'm a bioengineer. I still took my semesters of calculus. I still took my semesters of physics. And then now I do kind of stuff that's more related to mathy things in my major. So I think in the beginning, you do stuff that you're more familiar with in high school. And then as you move forward, you get to specialize more into stuff that you're more interested in.
Thank you.
Yeah, I can also answer that too. So I think like different fields of engineering will do different fields of math. So yeah, in the beginning, it's a lot more calculus oriented. So if you all have experience with calculus A, B, or BC, at my school, those translate to like Calc 1, Calc 2. And then you'll also be taking like multivariable calculus. So instead of just dealing with X and Y, you'll have a few more variables in there. And then you do some linear algebra, which is not to say that it's like algebra per se. It deals with like matrices and things like that. And then you have ordinary differential equations. which is
Oh yeah.
a whole bunch of fun. Yeah, Sarah knows. So those are like the main math classes, but math never really goes away. Those are just like formal classes, but they show up in all of your other classes if you're interested in engineering. But yeah, great question.
Yeah. And if you're like scared of math, I know that I was one of those people that was kind of scared of math. I'll tell you that going into college, math is a lot more fun because it's related to what you're doing. So like, for example, if you guys have ever done biology or you've like tried to do anything in biology, you know it's very unpredictable. You don't really know what's going on. So by using math, you can kind of predict the future. And the same thing happens for all the other disciplines as well. Okay. And 2 questions in the chat. Do you know if there are any jobs in STEM that are related to medicine? There are a huge number of jobs in STEM that are related to medicine. And I know this because I've done jobs that are related to medicine. So there are a lot of different avenues that you can go to. When you get into college, you guys have probably heard you can be a pre-med, which means that you're studying some biology-related discipline in college in order to go to medical school afterwards. You don't have to go to med school. I'm not a pre-med. So medical school will prepare you to be some sort of practicing physician in medicine. You could also be a researcher, which is kind of the route that I'm taking. And that means that I am the person or the part of a group of people that are developing the medicines that the doctors use. So think like Pfizer, think Moderna, making vaccines for the pandemic. That's kind of what researchers do. And then you can also do patient advocacy work. That's more stuff like on the clinical side of things, making sure the patients are taken care of. You can do regulatory things. You can do more business-oriented things like what I'm doing right now. There are a lot of different avenues related to healthcare, and it's one of the most rapidly growing engineering disciplines out there right now.
Yeah, with that too, we also have something called like drug delivery, which is another lab that Engineering Tomorrow does. So thinking about not only what makes up these medicines, but how are they entered into the body and how can we make sure that they're digested properly and are, you know, targeting the right areas and things like that. So yeah, really great question. Yeah.
Hello?
Hi.
Hi, sorry. Do you have any advice for somebody? I want to go into STEM, but there's actually so many like routes that I can go.
Yes.
And like most people go into college not knowing what they want to do. But so would I, but I don't, I feel like I'll go into college and I'll have more ideas of what I want to do. Like I won't limit myself. And like, that's kind of an issue because you have to choose one major. So it's like, did you guys, when you went to college, did you know specifically what you wanted to do?
I still don't know what specifically I want to do. It's not a big deal at all. Most kids, you're right, don't know what they want to do when they go into college. So I'll give you some advice about maybe what to do in high school and then a little bit more to do in college to figure out kind of what you want to major in. And then Emily, you can add on to that. So yeah, so in high school, I would recommend kind of just trying a little bit of everything. So what I did was I did projects in anything that I was remotely interested in. And with the internet, like social media and everything, you can look up pretty much anything at any time. Like if you woke up one day and you decided that you wanted to be a quantum physicist, you could probably go online and look up a video about quantum physics and just like watch it for the fun of it, right?
That's funny because I've done that. Like when I say
there you go.
things I want to do, like there really is, but I don't know. I feel like I won't be, because like, I don't know. There's so much to do. What about like with the overlapping of like different areas of engineering? Because if I wanted to do like with the mechanical and electric engineering, like those obviously overlap, but
yeah, that's
like
the fun
could you
part
get
about
a job in something, if you were to have a mechanical engineering degree, could you get a job in something that's more like electrical oriented?
Yeah, I'll pass it to Emily. I think she's got a good answer for this one.
Yeah, sure. I think Sarah was kind of alluding to this too, that engineering is super interdisciplinary. Whatever team or project that's being worked on, there's going to be several types of engineers that are doing those jobs. And what's really cool about college is that typically you'll have a survey course. So like you mentioned, you don't really know what you want to do yet because everything just sounds super interesting. And that's totally okay. When you get to those survey courses, you can kind of gauge a little closer, like, okay, what kind of job opportunities are available in this career? What kind of classes are these people doing? Do these classes sound interesting to me, or do they sound like a drag? All of those kinds of questions are things that you'll begin to ask yourself to kind of formulate, okay, what am I majoring in? And you can always have a minor as well. So like I said, I'm a mechanical engineering major, but my minor is in earth and environmental engineering, because both of those things are super important to me. Thinking about sustainability and the earth's resources, but also that hands-on component of machining and building things. So how can they put those together? Well, sustainability through machine design. So in terms of careers, if you have a mechanical engineering degree, but your minor, or you want to like electrical, if you want to be involved in something that's electrical, it really also depends on the experiences that you have. So for example, if you're, taking a lot of classes that are electrical engineering oriented for, technical electives or something like that, you can write that on your resume. These are past courses that I have that are, that would make me qualified for this position. So it's not too much of the title per se, it's more of the experiences that you have with that through clubs, through your own self-study, courses that you've taken, different things like that. But yeah, hopefully that helps answer your question a little bit.
Thank you.
Yeah, for sure. Sarah, we have some hands raised, but we also have questions in the chat. What do you think?
Okay, so let's answer the first two questions in the chat, and then we can go on to those who have their hands raised. So quickly, I guess I can answer this one. What diabetes treatments were you researching? So for people who don't know what diabetes is, there's type 1 and there's type 2 diabetes. And for type 1 diabetes, basically people need insulin. You guys have probably heard of that. They need to monitor their blood sugar all the time, and they need to take insulin, like literally inject it into themselves multiple times a day to make sure that their blood sugar levels are maintained at the right level. That's a really, really expensive, and it's a really just hard way of living. You have to always kind of be on track of what you're eating and always injecting yourself with this medication. So what I was doing and what CRISPR is doing is kind of making an automated system for doing this. So we created a set of living cells, you guys probably heard of cells in biology, that are gene edited to kind of sense their environment and produce insulin according to how much the patient needs. So what we do is there's this device that we can put these cells inside. We inject the device into the person. So it's like an implant, like a pacemaker or something. And it will be able to say, oh, this person's blood sugar is this level. We need to produce this amount of insulin in order to get them back to normal. And it does that automatically. So it eliminates the need for injectables, and it effectively acts as a cure for diabetes type 1, which currently has no cures. So that's one of the things that I was researching over the summer. And what do you enjoy most about being an engineer? Emily, do you want to start off? I think my answer will be very similar, and then we can move on to raise hands.
Sure. Yep, sounds good. So I think the biggest thing is just the creativity that comes with being an engineer. There's really whatever you can imagine, as long as it doesn't like break any laws of physics or, any laws of science, that, you can probably try to do it and try to figure it out. And that's something that I really enjoy about it, as well as like the collaboration, as I mentioned earlier. You're never really by yourself in engineering. You're constantly working with other people because, 2 minds are better than 1, 3 are better than 2. So just having those large teams and having those multiple fields interacting with each other kind of gets a holistic approach to different solutions. So those would be my 2 big things: the collaboration, but also the freedom that comes with being an engineer. But Sarah, what would you say to that?
Yeah, I would say kind of building off of that, just the impact that engineering has on everyday life. So I feel good knowing that the field that I'm studying is going to prepare me to help save patient lives in the future. Like with this type 1 diabetes work, it feels really good to know that I go to work every day, and because of what I do, one day we're going to have a cure for type 1 diabetes, or we're going to have a cure for leukemia or lymphoma or whatever the complex disease is. And it's the same thing with all engineering disciplines. They all have very real world applications. And it's just fun. It's fun to problem solve. So raised hands, Emily, I'm not sure if you know who raised their hand first.
Yeah, I think it goes in order. So scholars, academy, AP, if that's you all can ask the question.
Yeah, so we have a question. We were wondering how different AP level high school college classes are from actual college classes.
I also want to know, like, I heard one of you guys interned at like NASA and Con Ed. I want to know, like, if you guys got those internships while you're at high school, or if it was like the college that like connected you through like partnerships.
Yeah, so maybe Emily, I could take the AP question. You take the second one since you have
Yeah, sounds good.
interest in that. Okay, so for AP classes, I think it differs widely depending on what school you go to, but AP classes always, always, always give you a good foundation to go into the class. For example, MIT's classes are very, very difficult. I didn't get credit for my calculus class, so I had to take multivariable or I had to take like some accelerated version of single variable calculus when I got into MIT. It was very different because the problems that you're going to face in college are more application based, which means they're going to more give you like a problem and you're going to have to use the techniques that you learned in class to solve that problem versus them just giving you an equation and asking you to solve it, right? It's more word problems, which is more applicable to the real world. So I would argue that it's more fun. But for AP classes, every AP class I took that I later ended up retaking in college, even if it didn't give me college credit per se, it set me up very well to be able to start understanding those foundational topics and get me a head start in the class. So the class was still hard, but it was a lot easier than if I was exposed to the material for the first time.
Yeah, I'll answer your second question right now about like Con Ed and NASA, but yeah, I really want to second what Sarah was saying right now. Do the readings for your classes too. I think in high school I was like, meh, I don't need to read, but it helps you even further understand what's going on. And then you even have a stronger foundation to when you get to college and you're like, okay, I may not know how to apply this, but I know the concept behind it. So those are all really helpful things. But yeah, so for NASA and Con Ed, those are both college and things that I did in college. Both of them, one of them was through a connection that my school had. They have a like job posting website, kind of like an Indeed or Glassdoor just for Columbia students. So I was able to see that opportunity on there, and I was able to work as a summer intern, and then I was extended until the fall and part of the spring semester. So it was a pretty lengthy internship, and it was a lot of fun. I definitely learned a lot. And then the NASA program, it was just something that my friend had recommended to me. And they were like, hey, I think you would like this. You should try it. So I did it then. That one was not too much of an application. It was more of just like, if you're interested, learn more about this program and be involved in something that's like NASA sponsored. So it was a lot of fun. I know that I don't want to do aerospace now, but that's just as important as knowing what you do want to do.
I second that. Yes.
Alrighty, and thank you for your
for internships in high school. To address your last part, I didn't do any in high school. If you can and you want to, you should. I think it helps you figure out what you want to do. And like Emily was saying, even if you hate it, you know one thing that you don't want to do, which is just as valuable, if not more.
Yeah. Okay. I see the other school. We have MCHS.
Hi, I was just wondering like what your GPA and like SAT scores were to get into like your colleges.
I'm gonna have to think back on that. Emily, do you remember yours?
Yeah, so like I work in admissions, and like this is a common question that we get as like tour guides and people working at admissions. And like something that we commonly say is that like when you're applying to colleges, it's a very holistic process. You're not, the application and the admissions officers, they're not looking at just your SAT or ACT or GPA. They're looking at what you're involved in school, what you're involved in outside of school. Do you have any leadership positions? What do you do during your summers? Things like that. Your personal statements and kind of what, how is your journey and what makes you unique. So while SAT and GPA might be something that's looked at, it's just as important as anything else that's involved in your schools. So if like this is like pretty Googleable, like whatever schools you all are interested in, you can just kind of look up like common like average SAT schools for, let's say, Columbia. And then you can kind of see what the incoming years, what their average scores were. And then you can kind of gauge from there, like, okay, is this something that I fall in range of? Is it not? But just because it might not be somewhere where you fall in range, it doesn't mean that you won't get accepted in there. So like, for example, my SAT score was not that high, but my GPA was pretty high because I took AP classes and I was involved in a lot of leadership and extracurriculars on campus. So it kind of balanced itself out. So the number itself isn't too important. It's more about the contextualizing that and what else you're doing. But Sarah, I don't know if you have anything to add to that, or if you wanted to give your stats or things like that.
Yeah, so I will again stress college admissions is a very holistic process, especially after COVID. A lot of schools stopped paying as much attention to standardized test scores because kids just weren't able to take them. But yeah, if you want to kind of know general ballpark numbers of the scores that kids get, it's very Googleable. I remember I Googled it. But what I would focus on more is there are really two things that you need to stress in your like application essays in your application that are separate from test scores. And that is like focus, academic focus. So that you can show by taking AP classes, kind of challenging yourself, just taking classes that you're interested in, that sort of thing. And then the other thing that I would argue is more important than anything else in your application is passion. If there is something that you were really interested in solving, write about it in your application essays. So like for me, I tried a lot of stuff. I tried physics, I tried astronomy, I tried behavioral and social sciences, I tried movie making, I tried animation. I tried a lot of different stuff when I was in middle school and when I was in high school. And in the end, I kept coming back to biology because I really liked that ability to be able to influence people's lives and try and fix the world's problems through mechanisms that are already existent. So I wrote about that. I wrote about how I helped my mom in her garden when I was a kid. And that helped me figure out kind of the impact that biology can have on our lives. So any interest that you have, even if you haven't explored it super in depth, write about that. And then as for standardized tests, you don't have to submit your SAT if you don't want to. I did not submit an SAT. I submitted an ACT. And I don't know what it is, but for some people, the ACT is a lot easier than the SAT. And for other people, the SAT is a lot easier than the ACT. Like, for example, my SAT score was below the MIT average. But then I just randomly like woke up one day and I was like, you know what, let's take the ACT, I'm gonna try it. And I did way better on that test. I really could not tell you why. I think some people's brains are just wired differently. So when you guys are studying for these tests, one, you do study, you can use Khan Academy to study, and take both of them just to see which score you get a higher one on.
I am so sorry. I know that there are a lot of other questions that have not been answered yet, but our time for the Q&A is up. We're going to open the breakout rooms again. And I will say this, that in every breakout room, there is a college mentor. If you had a question that was not answered in this main room, please feel free to hop into your breakout room and ask the question there. There are a lot of experienced mentors. We had a couple of switches for your room, so you might be with a new mentor, but do not hesitate to keep the conversation going in your breakout room. And if you have trouble getting into your breakout room, just let us know. I want to say thank you to Sarah and Emily for leading such a great Q&A session. And thank you for all those schools that had questions in the chat and also in and also for unmuting and asking questions in the main room. Again, fantastic session, ladies. Thank you. Well, welcome back to the main room. I hope everybody is ready. Right now, we are here to start your wrap up, and we have the amazing Mr. Milton Davis, who's going to be leading your wrap up. And Mr. Davis, I'm gonna let you know, we've seen some amazing bridges. I think I see some on the screen now. So I think we're gonna have like a little battle of the bridges here.
Battle
So I
of
hope
the bridges. Let's go. We gotta, you gotta patent that. We gotta trademark that, Monica. Battle of the bridges. Let's do it.
Well, and you are
Nice.
here to facilitate. So let's go,
Oh,
Mr. Milton Davis, and start the wrap up, and the battle of the bridges may commence.
oh, let's get it on. Let's get it on. So welcome back. So excited to have you all on a special event day, building bridges to solve real world problems. And you know what we're doing now. We're having a wrap up to the bridges. So you all had a great breakout sessions with our Engineering Tomorrow college students. I know you are working on that engineering design process. I know you're failing and failing fast. You're making improvements as a team. You're testing. And we just can't wait now to see what you got. You know, basically, we just want to hear from you. You know, we want to hear how did things work? How did you improve them? What materials did you use? How much structure, how much weight can your bridge support? It's so exciting, and we'll make that a little competitive. Well, who am I? I'm Milton Davis. I'm here with Engineering Tomorrow. I'm a staff engineer, but I'm also curriculum coordinator, and I'm engineer at NASA. So we have a lot of experiences with bridges because we desire to build bridges in space. I know, right? We don't want to build huge structures in space, larger than the International Space Station, using a little additive manufacturing, but definitely using, trusses and arcs and different things to make them extremely strong. Maybe even have large structures like bridges on the moon. Maybe even have them on Mars. Yeah, we're excited about that. So what we're talking about today, again, what materials did you use? We know some common materials of bridges like concrete and steel and asphalt, but we know that you all had to really become creative because you're building really strong bridges out of things like popsicle sticks. I mean, you're really, really innovating. So before we jump in and just allow various teams to show off their awesome innovations, let me just hit you with one Slido question, just one. If we could facilitate this, Monica, what did you enjoy most about this lab? That's all we want to hear. So if you go to slido.com and you type in those numbers, you see them 3245703. We're going to capture this in real time on the screen. What did you enjoy the most about Engineering Tomorrow Bridges Special Day? Let's do it. Hey, and Monica, if you could test this out for me, make sure my poll is working, that would be outstanding. Oh, look at these schools, man, oh man. Is that all St. Peter's? I see you. Lori, Denny, I see you out there. Herndon, let's go. High School for Community Leadership, I see you, bro. Working it, nice. Wall Trip, I see you out there. Come on, Jason, Burdick, Sale High School, nice. Frederick Douglass and Upper Marlboro. Come on, let's do this. Come on, Scholars Academy. So somebody like engaging, they like bridges. Group collaboration, love it. Scholars Academy, good to see you. Holy Child Ride, nice to see you all out there. Building is coming in. Oh, Gina Carabin, NDA. Oh, I see a beautiful bridge. Oh, we see it. We see it. We're ready. What's up, Jason? Hey, buddy. Good to see you, man. Nice. SGRAC, very nice. Okay, good. We got, I enjoyed working in the group. I liked experiencing different engineering courses, the partnership, the friendship, excellent building. These are all the, what we're hearing? We're hearing everything from the engineering design process, building, we're hearing the research, we're hearing failing, trying again, excellent, collaboration, flexibility, tape, using the different materials. Yeah, this is great. Man, you all killing it, nice. Oh, who is this? Corin MCHS, that's a nice bridge. Look at the aesthetic appeal. Oh my God, we're ready to go. Let's do it, it's nice. Oh, they brought it. Gina Carabin brought it too. Friendship. Oh, this is great. All right. Well, with no further ado, let's do a Holy Child Ride. Let's get this thing going. I'm going to stop sharing my screen and we're going to highlight some teams. All right. Let's figure out who wants to be the first team to show off their bridge. Who wants to be and we want a demo if you can. We want to see it supporting some weight too. I see you, High School for Community Leadership over there getting it done. Who wants to be that first team? Holy Child, are you all ready? You ready? You want to talk through it with us? All right. Can we highlight the awesome Dr. Christine Bodil and her team here, and let's show that bridge. Talk through it. Let's do it. Oh, demo coming up. Oh, look at the colors. Look at the colors. Could we drop the camera just a little? If we could drop the camera. Yeah. Oh yeah. Oh yeah. Oh, first, before you test it, just talk to me about the artistry and any challenges you overcame. Talk to me a little bit.
Okay. Is it on mute or no? Okay.
No, we can hear you.
Perfect. So we wanted to include like a lot of the triangles, and we looked it up and it said that equilateral triangles were strong. So that was our thought process there. And then for the bottom, we thought that putting it straight across would be best, but we didn't want to like use too many. So we tried spacing it out as much as possible so we would have to do it again. And then each of these little support bars are 2 popsicle sticks thick and connected with duct tape.
Very cool. All right, that was excellent. And I love the colors too. I mean, add a little aesthetic appeal. Let's go. Let's see what you got.
Okay. All right.
I'm seeing some students with some cool hats on in the background too. I don't know what that's about, but I'm all about it.
Yes. Spirit Week and Holy Child.
All right. The good old Bush's baked beans. That's a heavy can. They're coming in strong, folks. Hey, they're coming in strong. You all got to come with it. They didn't start with a little can. This is like, what is that? That's like a 24-ounce can. Sheesh.
117 ounces.
117 ounces. Come on.
Okay. Hold it. Hold it.
You got it, Constance. I see you. Oh, that's nice. That's nice. Oh, you all are in trouble. Very nice. Are you going to add a little more, or you going to stop there? Uh-oh. Oh, I heard. She said add a little more. She said, I heard it. Maybe just one more can. Just dump it in there. Let's see. And then tell us your weight. And then afterwards, weigh your bridge and tell us your efficiency. Oh, look at that. Look at the flexibility.
We tested it earlier and we got like, you can.
Okay, so what's your efficiency then? What is that efficiency? If you divided the total mass you supported by the total mass of the bridge, what would you get? Let's see how efficient the bridge is. Man, this is great stuff. Oh yeah. Oh, look at those hats. Nice. Yeah, somebody, you got to get the calculator out. You got to get it out.
We don't have the weight of their bridge yet, so we'll put that in chat when we get it and let you move on to another group.
Thank you, Christine. Outstanding job, Holy Child. You all killed it. All right, next team. Who's up next for me, Monica and Constance? Who do we got? 117. You got to beat that. Who's the next team? Come on. Oh, I see All Hallows raised their hand, and we want to highlight them. And then we're going with Frederick Douglass. I saw them. They're ready to go. All Hallows, come on in. Let's do it. You all ready? Highlight. Are you ready? Are you ready? Are you ready? No? Are you ready?
I saw More Catholic had their hand up.
Okay, let's go More Catholic. Let's do it.
All right.
Come on, let's do it.
Is More Catholic ready to go? You guys turn on your camera so we can pin you to the main screen.
I've never seen so much engineering power. I mean, they are having at it. You see it? Look at Heights High School. Look at them.
All right. I don't see More Catholic turning on their camera. Who's ready to go? Oh, there it is. Now I see it. All right. I'm going to spotlight you and then please unmute so we can hear you.
All right. How you all? Okay, there we go.
We have a gallon of water. Bye.
Wow. Hey, how you doing? Nice.
Put the cap on. What are you doing?
Yeah, you got to put the cap on.
Hold on.
You got to put the cap on. You got to put the cap on. Let's do it.
Oh, you twisting shit down. All right, let's go.
Oh, you're going to do an entire gallon of water.
Here we go.
An entire gallon. Sheesh.
Watch it break this time.
Kind of. Oh, man.
Oh,
Hey, it's okay to fail. It's okay to fail.
we're not failing.
Oh, with that, did you hear it? We're not failing. Nice. Awesome. Oh, that's nice. Oh, look at that. How much does a gallon of water weigh? You got to tell me that. How much does it? Oh, you're gonna do another one? All right, let's do it. Let's do another one. No,
This
what?
one's just for decoration.
What? All aesthetic. Okay, that's nice. Very nice. Very nice. All right. Great job. You want to go? Are we ready for another school? Great job. Tell me.
Yes,
put your
Heights High School
efficiency in
said
the
they're
chat.
ready.
Let's do it.
Where's
Heights. Come
High
on.
School? Here we go. All right, we're gonna.
And don't forget, every team that presented, we want to know your efficiency in the chat. Tell us how much
Heights
your
High School,
bridge
unmute.
weighed. Yeah, come on. All right, talk to us about your design. Like, what were some challenges you overcame? What materials did you use? All of that good jazz. And then give us a demo.
So basically, we got some more materials, and we used it as the floor, right? And it's pretty strong right now, but it's kind of bendy. And
that's all right.
With the power of tape, we just kept on going. And
okay. How much weight? How much weight?
Right now it's probably about 20 pounds.
No, that.
Did you hear that?
15.
15.
Yeah.
15 pounds. Sheesh. And you're still going. You're going to add a little more now. Wow.
Yeah.
Look at that. What are you using? Is that sand or gravel?
Cat litter. It's cat litter.
Oh, nice. Nice. Very nice.
Good morning, Georgia. Today is Wednesday, September 28th.
Great job. Hey, we'll go to the next team. Great job, you all. Very nice, high school. Okay, we got another one. Hey.
First line is up.
Very nice. Wait, don't get out
Can
the
you
camera
guys
now.
unmute?
All right, who's gonna talk us through this awesome design? I see some serious trusses going
I'm trying
on.
to gather my students to talk about their bridge, so hang
Talk
on one
about it.
second.
Let's go.
All right, where are my students? Enter frame.
Are you gonna talk?
Okay, all right, so we've got a nice colorful bridge. I'll move closer so that you can see. Can you pull this
Thank
closer?
you very much. I love seeing an all-girl team as well. You just can't beat it. Let's go.
Oh, wait.
Oh, I
Okay,
see
here
some
we-
nice colors in that bridge as well.
Yes, we
Yeah,
spent some time decorating, which was
What
nice.
was the most challenging part of developing this beautiful bridge you have?
What was the most challenging part?
Probably trying to like level, like we built separate parts, so like trying to make sure that these were leveled and they would stick to the base.
Good point. Great point. All right, are you ready to test it?
Yes, so just give us 1 second. I'm gonna put the camera back here for a second.
Okay, good deal. Hey, thanks for Ursuline School. Thanks for having us as well. We
Oh,
appreciate
thank you. Great so far. So I'm going to just poke a bag on here.
Oh, they're getting it ready. They're getting it. I see they have the nice strap there on. See how much weight. They're making bridges real time too. I see someone's making a bridge right now. Uh-oh. There are a lot of schools ready to go.
Wait, the bag. Get some like pencils. Get the scissors.
Scissors, one for scissors.
Oh no, those are and those are
Let's just put the green stuff. Oh God.
All right, weighing it down. Hey, give it some weight. Yeah, throw some. Okay, there we go. It looks like a brick. It looks like it's not moving at all.
Another pair of scissors.
Very nice. You all are killing it.
What about some tape?
Yeah, just throw like a can, anything. That bridge is strong.
Keys.
Okay, all right. Look, not budging. It's not budging at all. Great job. Let's give it up for Ursuline School and let me know the maximum mass. When you are done, let us know the maximum mass. We need to know that. All right, next school, Frederick Douglass High School. Hey, I'm in Upper Marlboro, Maryland as well. I'm in Upper Marlboro right now. You didn't call me to come by. I'm sad. It's all good.
You're welcome anytime, Milton.
Okay,
Anytime.
all right, let's do it. Okay, thank you.
Come through. Now, okay,
All
so
right, I'm coming.
Cool. All right, what's your group name? 4PF. That's our group name? No, it's Three Musketeers. Three Musketeers. Their bridge weighs 198 grams. So far, they have held, here. So far, they have held 7 500-milliliter water bottles. And we're going. So far, they are 7. All right, so we got 8.
Wow.
9.
Wow. What? The Three Musketeers killing it.
10.
Nice.
11.
Uh-oh.
Running out of bag space. 12.
Oh. Okay. It's bending a little. It's bending just a little bit. Okay. Hey, I love it. No fear. Look at this. No fear at all.
We are out of bag space.
Wow, great job.
Bottles so far, and we are out of bag
Very
space.
nice. Excellent job. Great job, Frederick Douglas. Okay. Excellent job. Okay, now we got St. Agnes Middle School MO. Let's go. How you doing? Hey, how you all doing? Yeah. Oh, I see. All right, talk to us about this beautiful design. Look at that. I see you, Holy Child, 47.9 efficiency rate. Great. Who's going to talk to us about this design? Who's talking to us?
What did you guys do?
Yeah,
Okay.
like, how'd you come up with this design? Like, what were some challenges you had to overcome?
Because at first we thought it was like going to be way too sturdy, so it would like snap in half. So then we put tape to make it better.
Oh, okay, cool. Love it, love it. All right, so you're adding some books to the back. How many books do you have in there right now?
3.
3 books. We're up to 3 books, everyone. 4, 5 books. It still doesn't look like it's bending yet. 6 books. Okay. Wow. 7. Okay. I see a whole stack coming. 8. Let's do it. 9. Okay. 10. How we doing? Wow. Wait. 11. 11 books. 12 books. It's not moving. 13. All the teachers brought like some serious books over. Is that 15? Sheesh. Okay, we're dumping in the big books now. This is like a thesaurus.
Put it in there.
The teacher said, just put it in. Just go for it. Oh, did it bend at all? Nothing. Sheesh. Some serious bridges here today, man. And look at the design. It's like the bigger the triangles, the better. Awesome. Outstanding. Outstanding, man. Killing it. You all are building some great bridges. Let's do it. Very nice. Okay. They're still going.
They're still going.
Wow. This is serious. Are we still recording? Man. Excellent job. Clap it up for St. Agnes. Man, outstanding. That is a super strong bridge. And look at the aesthetic appeal. Did you see the runway street that they show? That is very nice. All right, we got Scholars Academy 901. Is that who we're focused on?
Oh, here we go.
It's their turn. Okay.
All right, we're on.
I gotta go to new school.
You gotta zoom in. You gotta come just a little closer, just a little bit. Can we come a little? Yeah, yes, perfect, nice. Okay, this bridge, man, look at the
And if you
look at the civil engineering, man, very nice design. Somebody's got to talk about this design. Come on. Come on, somebody's got to talk. Yeah, we can see it. We need somebody to talk through this design, please. Hey, how you doing, man? Scholars Academy.
Okay, let's go back.
Bro, there's high schools on there.
I think. All right, we're ready for you. Scholars Academy, who's going to talk through this awesome design? Let's do it.
I think they froze. I'm gonna.
Oh no.
Yeah, I think they're frozen. We're gonna go to the next school. So the next school in line was Notre Dame Academy. I'm trying to find their little box. I can't find them.
Sorry, Scholars, we're coming right back to you, Scholars. We're coming right back to you.
Oh, I see you now. All right.
There's 2 Scholars Academies. All right. Okay. Oh. Oh, yeah. Looking good, man. That's serious. Talk to us. Talk to us about that design. You got to talk to us now, man.
We did triangle.
Okay, they're saying, wait, we're not talking. We're just going to show you. The proof is in the pudding. No talk. Let's get it. Okay.
Anything's putting this.
Okay, they're adding a lot of weight. I'm not sure they can hear us, but they're having at it. That's good. Look at that, more and more. Looks like soap bottles, they're coming in. Yeah, this is an intense battle, isn't it? This is like you said, Monica, battle of the bridges. We are going. Man, imagine the skills you all have to build bridges across the world. You're going to hear from an outstanding presenter very soon in Avery Banks. Who's going to talk to you all about bridges, but you all have some skills to get on her team for sure. Oh, they keep bringing it. They're bringing in some tape. There we go. Very nice. They can't hear us, but they're killing it for sure. Awesome. 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 Very nice. Great job. NDA. This is Gina Carbon's team. Excellent job. Let's clap it up for them. Okay, we got Sacred Heart High School. Let's do it. Ooh, I love the get up. I need one of those hats. I need one of those sweaters. Send me some swag, please.
All right, so which one of you wants to talk about it?
So we built a cable stayed bridge. Our cost was $74.80.
Did you hear that? Our cost. First team to talk about the cost. Let's go. Great job. Okay.
All right, so our first weight is 32 ounces of water.
32 ounces. We got a couple pounds jumping in here now. Oh, look at that.
All right,
Okay.
and then we're gonna add another 24 on.
Oh man. Oh, this is a very creative bridge. I like you got the tension. This is the tension bridge. Very nice. Are you
So
gonna
those
keep
were the
going?
only- Those were the only weights that we tested everyone on. So that was kind of our limit.
Okay. Well, tell me this. How did you all come up with such a creative design? I see just the aesthetic appeal. How'd you come up with this?
So we started by building the base. We weren't 100% sure where it was going to go. And then we kind of realized that like the best way to support it would be to do the cables.
Okay, great. Very nice. Well, clap it up for Sacred Heart. Very nice bridge. And when you're done, put your efficiency in the chat. Divide the total weight you supported by the total weight of the bridge, and we would love to highlight that. Great job, Sacred Heart High School.
Thank you.
All right. Clap it up for Sacred Heart.
I did high school for community leaders next, but their camera's not on, so I want to go to Wall Trip because they look ready. So Wall Trip,
Okay.
are you ready?
And we
We
have
already
another
actually-
team to go back to
All
as
right.
well, right? All right, come on, let's do it.
What happened?
Ooh, you all have like a real setup. Wall Trip is ready. Look at that. All right, who's talking to me? Who's talking about this design? There we go. Hey.
All right, so we use cardboard to reinforce it, or like as a base, and then we put the sticks to make it stronger. And then on top of the sticks, we use the popsicle sticks, and then we reinforce it with tape just to make sure it's like perfectly strong.
Oh yeah, the colors, man. It's a beautiful. It's sleek. It's sleek. Oh yeah. All right, you ready to test it?
We maxed out at 165.
Cool. How much mass are you supporting right now? Are you going to test it now?
It's holding a 5-gallon Home Depot bucket.
Okay, let's do it. Okay. Look at that setup. Look at the setup. The perfect dimensions. They are getting this thing going. I think we got 2 bottles in there now. Is that 3? 3?
2. That's 3.
Wow. Very nice. Oh, look at it.
That's a
Oh,
shop.
man.
It looks like a shop.
Yeah, that's serious.
This is our fabrication laboratory.
Very cool. I'm jealous. Please invite me.
You're invited anytime. No,
Thank
no.
you.
9.
Look at that. Nice. 9 bottles.
Let me know when you're
10. Wow. Okay, we only have 5 minutes left. I don't know how many more teams we can do. This is great. They're killing it. Come on, Wall Trip. If we miss any teams, please record a video of what we just did and share it with us, please. We want to see it. Yeah, we'll go with one more group and then I'll have some wrap-up slides for you all. But Wall Trip High School, you absolutely killed it. Wow, look at that. A 5-gallon container full of water bottles. Overflow of water bottles. Very
I know the high
nice.
School for Community Leadership wanted to go next and they weren't ready. I just want to
Okay.
make sure I grab the right screen.
All right, that's the last school, and let's
That's the
clap it up
last
for
school
Wall
we're gonna be
Trip.
able to, so
Go ahead,
it's-
Wall Trip. Yeah. Oh, there they are. Okay. That's a nice bridge as well. It's looking good. It's looking good. Bridge is looking nice. Okay.
We have about 10 pounds, I think, 2 textbooks. Where's the hook?
Is anybody gonna talk to us about the bridge? That's a nice looking bridge. It's creative. It's creative.
Mine is on the side. So, that's 10 pounds, 2 textbooks.
10 pounds.
Give me another textbook. See, I have the backs from last year.
Very cool. Oh, wow. Let's go. Engineering Tomorrow Legacy. Legacy teams. Shout them out.
That's 15 pounds.
15
the girl said
pounds.
that's it. One more to go. Give me another textbook. Hurry up, hurry up, hurry up.
Oh, Sacred Heart, 92% efficiency. Nice. Okay. They're getting more weight. They're getting more weight. That's
All right, I
good.
got another textbook. So we're up to 20 pounds.
Wow. Very cool. Very, very cool. Great job. Let's clap it up for high school for community leadership. Excellent job. Well, I can't say enough. Let me just transfer right back over to the presentation. We have a very nice guest speaker coming up for you all very soon. Oh, I see her on that's the buddy from last year, Avery Bang. What we wanted to talk to you about real quick is what you should be really focusing on with these bridges. The reason why we're harping on structural efficiency is because it's not just, and Avery's going to talk about this, it's not just your ability to create a very strong bridge. Can you do it with limited resources? Can you do it in an area that has limited resources? And that's where Avery Bang is going to talk to you all about. But we're going to also, we want to say this. Sometimes when you sell products, you got to have some sort of aesthetic appeal. And that's why we keep highlighting that. You know, we talked about the cost, that's important. We talked about limited materials, but it's also cool as engineers that we can truly, truly innovate, right? You can truly make it, you can meet the requirements. It can be really strong, but it can also be something that's truly a work of art, which you see in the bridges that I'm sharing right now. And lastly, in the interest of time, this is a great career to make some money in. You know, engineers do very, very well. They're in high demand. But trust this, if you're developing a product that's improving people's lives and you love doing it, you're going to be just fine. And you don't have to wait until you are in college or after college. You can obtain internships right now. You want to learn more about that? Get in touch with Constance and Engineering Tomorrow. We'd love to talk to you about those opportunities. And last but not least, let me introduce you all to a very outstanding engineer and innovator. This is going to be our guest speaker in Avery Bang. Avery is a renowned engineer and entrepreneur and public speaker. She's a board member and the past president and CEO of Bridges to Prosperity, a nonprofit social enterprise providing isolated communities with access to essential healthcare, education, and economic opportunities. Without further ado, let's all clap it up for our guest speaker today and an awesome individual, Avery Bang. Thanks for coming today, Avery.
Milton,
I'll
always a
turn it
pleasure.
over to you. Always
Yeah.
a pleasure.
Good to see you again. You're
Good
the
to
best
see you
MC
as well.
of any event. I kept being like, I need to call Milton and MC all the things that I don't get to do. But
It's
I'm
easy
so
to MCU. It's easy to MCU.
It's been such an impressive morning. I was watching some of those loading conditions, and I just want to say that like the teams, you guys have done just an incredible job, you know, making magic. So I need to be able to share my screen, and I hope to be able to do this well and quickly.
Oh, you got it.
All right, we can see it all right. Ready to roll?
Yeah, looking nice.
Okay, so I know a lot of you guys are out there working on your bridges still and cleaning up. So I'm just gonna hopefully be able to inspire you a little bit about why bridges are important. And it's not only for being able to become, as Milton said, you know, structurally proficient and getting your efficiency ratios down and up there, but like, how can you actually make beautiful structures? And how can you make structures that change the lives of people around the world? So I graduated college and this was my office, sitting on rural infrastructure in the middle of Nicaragua. And, you know, I think a lot of people say, well, Avery, how did you get that job? And like many of you, I was an aspiring engineer, but I kind of imagined, well, I don't know, maybe I'm going to be in front of a computer a lot. Maybe I'm going to be using a calculator a lot, which I do. But I also have the opportunity to actually go out and touch, feel, and build the things that I design. And I think that that's one of the things that I love most about my career in engineering. So I wanted to share a little bit about my story today in hopes that maybe I could speak to a few of you to maybe become bridge engineers, or at least just to consider all of the worlds of opportunity that the STEM fields open to you. So this will date me a little bit. I'm quite a bit older than all of you, but Legos were also popular in the early 1980s. And I remember thinking like, wow, I like to tinker with things. And, this is really before robotics got big. And so most of my friends would just like sit there and build castles or houses or bridges in this case. And so as I started to think about what it was that I wanted to do in school, I was like, well, I also love to be creative. And just like many of you, that last bridge I saw was really cool aesthetic with that architectural feature on the side. Kind of imagine maybe, doing something artistic in school. But ultimately, got to kind of the decision point of what I was going to do, and I decided to play a collegiate sport. And so I'm not sure how many folks in the room are thinking about playing sports in college, but you have to kind of take all of these factors into play and decide like, what could I do next in my career that's going to set me up? And for me, I felt like having a scholarship was really a differentiator for my ability to afford to go to college. So I decided to go to the University of Iowa, play soccer, and double major in engineering and art. Going a little slow for me today. But halfway through my college years, much to my mom's chagrin, I decided to buy a one-way plane ticket to a place in the middle of the South Pacific, which frankly I had to look up on a map. I went to Fiji. If I was in a room with all of you, I'd kind of ask who's been to Fiji or whose parents honeymooned in Fiji. You normally hear kind of a smattering of kind of folks who all think of Fiji as a beautiful white sand beaches, really wealthy. But the reality is it's much like the rest of the South Pacific. There's a lot of nuance. There's both great wealth and incredible poverty. So as I was in Fiji, I found something that I hope each of you find in your lifetime, and that was a deep passion, a passion to wake up every morning and be excited. And I did that because not laying on the sandy beaches and getting a tan or hanging out, having a cocktail because I was underage, but actually doing something that gave back. It wasn't just about me. I didn't just want to go have a good long vacation study abroad. I wanted to help people. And how that came about was I was volunteering for the Breast Cancer Foundation. It's a little branch there in the islands. And every morning we would get our books and our bags and our translators and our packets, and we would want to go out and help all of these rural communities and all the women in these rural communities understand the importance of breast cancer detection and early breast cancer detection. And so we would get to these rivers, and after you've driven for 2 hours, and then you take a little tuk-tuk for another half hour, and then you walk for 30 minutes, you'd get to a river. And at that river, you decide, do I want to risk my life today to go across that river to help these women learn about early breast cancer detection? Or do I turn around because it's too risky? And this is a picture of me the day I found my passion. It was the day I walked across just something so simple as a bridge. For those of us living in the United States, on average, we actually cross 27 bridges every single day. And so you almost don't think about it. You're going on an overpass, you're going on a bike trail, you're going over to like a major, I'm sitting here in San Francisco overlooking the Bay Bridge. Lots of different structures that are visible and not visible. But when you're living in a really rural area and there is no infrastructure, a bridge was a huge difference maker. And for me, it clicked. It was like, I could be passionate about helping people be connected, not about bridges, but about connection. And I like to say that at age 20, my world really opened up and began. I made the decision to go back to college. I'd left halfway through to study abroad. And so I flew home to the University of Iowa and got to work. I got to work talking to my professors, to my friends, to people in the community, and talking about there's this huge need around the world where people can't cross rivers. And I convinced an organization called Bridges to Prosperity to let me go build the bridge with some of my closest classmates in college. This particular crossing, you can see on the right, is in the highlands of the Peruvian mountains. So we're talking, if you fly into Lima, the capital, and you take another 2-hour flight to Cusco, where Machu Picchu is located, drive 6 hours on the tops of windy mountains, and then you walk 3 hours into the kind of ravines and the crevices, you arrive at this community called Yavina. And in Yavina, every single year, when the water is low, like in this picture, all you do is you take all of essentially the vines that have been on the hillsides, and they braid those vines. And as you can see, those vines get anchored on either side with a large mass, i.e. rocks, and kids cross those in order to get to school. Farmers cross those to go to markets. Women cross those to go to the doctor. But every single year when it rains, and we're talking not just one day, we're talking 4, 5, 6 months of the year during the monsoon season, those braided vines get washed away. So imagine, here I am in the schoolyard and with the children in the dry season, having just watched all of these kids cross this bridge. Only half of those kids are going to be there for the other half of the year. And so the story of why bridges impact the lives of people around the world just clicked, and I ran with it. I built this bridge in Yavina, Peru, and I found a sense of purpose. So anyone can be excited about a lot of stuff. You know, I think probably Milton and I are both excitable people, I bet. I don't know that for sure, but like I can get excited about playing soccer, I can get excited about my paintbrush, I can be excited about my Legos. But when I found something that was bigger than myself, that I was doing for other people, creating a sense of why to get up in the morning, it all changed. And that's something that I think STEM careers can do in spades, whether you're designing the brand new Apple Watch, like one of my mentees here in the Bay, or whether you're designing a bridge for a bunch of kids in rural Rwanda. There's a sense of purpose that I think engineers get to have that's really, really unique. And for me, that sense of purpose started to open my viewfinders. How big is this problem of rural isolation? It's big, guys. It's real big. We're talking communities in Pakistan, communities in Nigeria, communities in Colombia, communities in Indonesia, communities in Ethiopia. The ways that people get to school risk their lives every single day. And I had the opportunity to experience that firsthand right here in rural Ethiopia in Bahadar. 10,000 people live on the far side of this bridge right here. And what's interesting is bridges are so critical is that back in the 1400s, when the Portuguese actually, for any history and or geography buffs, here's a tangent for you. In the 1400s, the Portuguese built a series of bridges over the Nile, the Blue Nile in this case. And their multi-arch spans were built a little bit later by engineers. The binder is egg, which I think is so interesting. There was no such thing as cement at the time. So they use egg to make it cementitious, to make it connect all of the rocks together. But anyhow, in the 1938, as the Italians came across Ethiopia and this entire community of Gondar is saying, hey, don't come, we don't want you to invade. They got out there with their picks and their axles and they self-destructed that bridge that had been there since the 1400s when the Portuguese built it. Better to keep them out than for us to be able to get across. But the unintended consequence, or maybe the known consequence, is like any piece of infrastructure that becomes critical, it being gone is so much more obvious. So since 1938, the only way for 10,000 residents of Gondar to be able to get to primary school, which is beyond, or secondary school, which is beyond 4th grade, the only way to get to healthcare, the only way to get to the big regional center is to get 6 of your best friends on either side of a river, hold this rope. So if you cannot see this screen, go poke your head close to the screen because this is wild. And have 6 of your friends hold either side of that rope. Just think about how terrifying it is if you cannot see that river, how far down below. And that is what kids do every single day. Women do when they need to have an emergency and get to the hospital when they're birthing a child. That's what people do when farmers say, I've got just a little bit extra I want to sell at the market. And so when Bridges to Prosperity came in and built this bridge, I saw a couple of suspension bridges here today. I'm really impressed. They're much more technically challenging intellectually and kind of psychologically, but they are really efficient. And so if you start to think about If you look in the lower left-hand corner where that multi-arch span, we initially did a simple kind of crossing. The year one, we actually put a truss structure, which I saw a lot today as well. Trusses are very efficient. The series of triangles are probably the most efficient bridge structure, but they're heavy. But the reality was, in this case, the water had risen so much since the Portuguese originally built this bridge that it now crests over the top of this bridge every single year. And so something interesting about engineering is it's a dynamic set of problems you're constantly trying to solve for. So when the organization before me went in, they initially said, let's build a truss bridge. Let's, essentially anchor it to the existing multi-arch span, and we're gone. Then very next year, the water rises. The water has such incredible lateral force, and lateral force just means force coming in this direction as opposed to a weight coming down direction, that it ripped from its hinges and it washed away. And so what we were challenged as engineers was then, what do we do? And the solution was a cable supported structure that wasn't right there at the local area of fixing, but much further up into the canyon, to put it on either side of the canyon wall and to lift the load off of the floor. Really interesting, but to this day, 10,000 people, residents of Gondar, the very same people who built this bridge with their very two hands, are using it to access all of the aforementioned services. I figured by now, you guys are probably tired of all the building and the deconstructing and the weird girl on the video talking to you about bridges. So I thought I'd show you a very quick film that hopefully shows better than I can tell. All right, so that's a little plug for a film that you guys can find on Netflix called Dream Big. It was in IMAX theaters across the country for a few years, but coming back to the point, it's all about the people. That film was not about how much cable tension was in that strand or how much weight was in the anchor or how big the walking surface was. That's the stuff that the engineers, we all talk about and think about every day. But the reality is, whether we're designing something new for the space station or we're designing something for people in rural Bolivia, we're all focused on people. And that's the thing that I feel like is maybe lost when we start talking about STEM fields and engineering in particular. We talk about proclivities for science and interest in math, the ability to solve problems. But there's also a huge people element. We're all helping people every single day. And like doctors, like nurses, like teachers, engineers have a profound impact on the world. And we're helping make the lives of everyone better, even if they might not even know it. And so I like to kind of bring this all together and just say, imagine if you had to risk your life to seek opportunity, to come to school today, if it was a decision if you may or may not make it home tonight. And I'd like to encourage you to think about, there are 1 billion people on this planet that is their reality. That is 1 in 7 humans today cannot decide to go to school or not based on their ability to risk their life. Engineers have the capability to solve that problem. When you build bridges, kids go to school, we get jobs, farmers are more profitable, healthcare is better. And for those of you that are excited about the humanitarian sector at large, the United Nations has Sustainable Development Goals, and the SDGs can only be solved when there's connection. Whether you want there to be economic growth, reliable, affordable, clean energy, gender equity, there is, like everything, transportation infrastructure is actually at the root of solving many of these global ills. So at Bridges to Prosperity, we envision a world where poverty caused by rural isolation no longer exists. And I'm inviting some of you to be part of that movement, whether you want to be a bridge builder or an engineer or just in the STEM fields at large. We're trying to build a global movement of people that care a lot about sharing our skills and expertise on a global scale. To date, we've actually built, this is a little outdated, sorry. We've built over 400 bridges across over 20 countries. And every single day, we have over 1 million people walking across these bridges, all because of people like you. People who woke up in the morning and said, I'm going to build a technical skill and I'm going to use that technical skill for good. We believe it's really important to say it doesn't just feel good, we think it does good, but to also do research. So for many of you, you might actually not want to be an engineer, but you want to be more of a researcher, you want to be in a lab. Well, we partner with researchers at the University of Notre Dame, Yale, Arizona State, and others, University of Colorado Boulder, to set up research studies of really what the impact of infrastructure is. And I can just say it's really impactful and profound. So there's a lot of roles that you can have with the STEM field to help bring attention to the impact that's being helped for. Our big idea right now, so I want to kind of get some people excited about, is that we're actually solving the problem of rural isolation in the entire country of Rwanda. And I hope you guys understand, this is not Avery flying in and doing it. This is the government of Rwanda with Rwandese engineers, Rwandese managers, Rwandan foremen and superintendents and local folks who are going to build that bridge every single day, who are designing and building these structures with the help and the background of our organization. But we hope to scale this globally. And we're currently in our 3 years out of a 5-year program, achieving that, what we originally thought was an impossible dream. And I think it's kind of interesting for folks who have not spent much time thinking about the continent, is that Africa is quite large. It is not to be thought of singularly. This is not like you can think of Africa. East Africa in its own right is very diverse and is larger than the United States. And so Rwanda, located here kind of in the Central East region, is one of the smaller countries. And if you can imagine, it's a very hilly and mountainous country, almost like they call it the Switzerland of Africa. It's clean, it's beautiful, it's safe. It's one of my favorite countries in the world. But as you get into the more mountainous regions in the West, that's where communities get poorer and poorer and poorer. Because why? It's harder to get places. The rivers are wider, the mountains are bigger, it's harder to get to and from commerce. And that happens to be where we are focusing our efforts, building the most bridges. So with that, I didn't want to belabor the point too long. I am a structural engineer by training. I could talk to you about all of your designs until we're blue in the face, but I know you guys have all got that in spades. So I just wanted to join you this afternoon or this morning, depending where you are, and hopefully show you a way that STEM fields and engineering in particular can help save lives around the world. Well, thank you.
Oh, wow. Thank you so much, Avery. Can we give it a huge round of applause for Avery Payne? That was outstanding. Unbelievable. I mean, well, we can also offer up a little time for Q&A. I think we have a couple of questions answered, Avery, in the next 10 minutes. But I mean, just the inspiration to know that you can use your skills to change someone's life. I'm motivated. I want to be a part. Can I be a part of your team? Sign me up.
We're taking astronauts and NASA all the time, so sign up.
All right. Cool. Any questions? Does anyone have any questions they want to either put in the chat or they want to unmute themselves? Any questions for Avery? I see. Thank you so much. They really enjoyed this. What an inspiration. Thank you, Avery. Amazing presentation. Amazing, Avery. Thank you for sharing your experiences. Yeah, that's good. Any questions at all? I would want to ask Avery some questions. Any questions? If you all don't ask, I'll ask. If
Avery.
You all don't ask. There we go.
Avery, we're curious to know where the funding comes from.
Good question. So we're funded mainly by foundations, actually. So if you look at the pie of how much it costs to build a bridge, over half is from the local government, up to 80%. But then let's just talk about how does Bridges to Prosperity come in and support the other part. And most of it is foundations. Good amount of it is like corporations. So we have some of the biggest architecture, engineering, and construction firms in the world that support us, and also sometimes build these bridges to help us innovate. And then a small sliver are individuals. We actually have classrooms, sometimes do fundraisers. We've got individual people that say, hey, this is something I'm excited about. But we are really pretty lucky and fortunate that we are not very good salespeople, but the money seems to come. So I'm doing pretty well.
Great question. Great question. Anyone else? Anyone else?
I've got a technical ad because I always go too fast when I'm excited. So I clearly like you guys. I'm very excited going fast. So there's two types of bridges that we really like to talk about. And so as you guys think about the structural components, the only slide I have that shows this is, here's one is a suspended bridge. So as you guys think about load and load transfer in a suspended bridge, we talk about these kind of like Indiana Jones style. So you could take a piece of rope and it's a parabola essentially, and let the weight in the middle kind of hang. But the reality is the weight is not being pinned right there on the top of the anchor or the top of the handrail. It goes back. And so what's interesting about that is that you have a lot of load. These anchors end up being so big because if the tighter you pull that string, think about the tension you put on it. It's harder and harder to hold up that weight. And the more and more weight you put on, the more you gotta do. So there's a huge anchors into these hillsides, which is actually 90% of the cost and effort, honestly, is in the getting the labor to dig huge holes. And we're doing this all by hand with picks and axles and these things, and backfilling it with rock, aggregate, cement. The other kind of structure that we do, you guys saw in the Dream Big film, is a suspension bridge type. And so those are different. So that's like here in the lower right. I wish I could show you in the front, but you have, just like the Golden Gate Bridge, 2 pylons on either side. And the load is actually coming into those pylons, and you're trying to drape the cable equally there, but you can see the cable in the back stay. And so what we say is that, like, you want to make it so as the cable goes in the front and the cable goes to the back, it's almost equal, because you don't want it to have out here and then right here, because then the load on this guy is going to tip. So it's actually a geometry problem, and it's beautiful geometry. But then the anchor, actually sizing wise, it takes a different kind of load. It's a little bit more of an uplift load than it is a rip out load. And so things that you guys can start to think about in your own structures is, how do these connect to the earth around them? Even though right now we just kind of placed them, and you guys did a good job of showing kind of, you know, how to make sure that it could clear your loading condition. But in the real world, what we call soil structure interaction is actually a very complicated and interesting part of bridge design.
You have 2 questions in the chat. Someone wants to just ask the question, but that 90% of the design and structures and the support, the anchors, man, that's deep. It's
time. It's a lot of time.
Okay, jump in. Who has those questions?
Say hi.
Hi.
We were just wondering, in what rural areas in the United States have you worked on bridges?
Yeah, so we focus predominantly overseas, but we do consulting in the US. So Appalachia is the area where you're going to find still people that live in the walking world. And that's kind of our target market. And so we'll consult and help on projects. Like I did one out near Gatlinville in Tennessee. I know we've got a sister organization that does some in West Virginia. But we really say that, like, although there is need in the United States, a lot of that is going to be covered with existing resources and know-how. You know, there's kind of the technical prowess within the country and the capital to make that happen, should there be the political will. In places like Rwanda, as an example, there's all of the intelligence, but there's often not the backstay of the resources or the procurement of those materials, and there's not necessarily the budget for it unless you have a new allocation of capital. So we focus more on the global South, which maybe you've heard of as like low-income countries or developing countries, because we think that we have the biggest opportunity for the biggest gain per dollar spent. Good question.
Thank you so much.
Yeah, of course.
Excellent. Last question is your favorite bridge that you've ever designed, if you have one.
Well, you know, it's kind of one of those things. The first time you do something is always really memorable. So that project I showed you right in the beginning in Yavina, Peru. You guys, I wasn't that much older than you. I know probably 20, 21 sounds like much older than many of you, but that's only a few years away. And that was when I built my first bridge. And wow. It was, you know, I'm now 38, to give you a sense. That's almost half my life ago. And I think I've always been really passionate about that community. I've gone back a number of times. The little boy walking across those vines, Rolio, is now an adult, you know, and so it's kind of interesting to see the evolution of what I call impact, like how that impacted his life and those of everyone else. So that was probably my favorite. Definitely not the hardest or the most complex, but you know, the first.
Excellent. Well, let's clap it up again for Avery. Outstanding job. I love the highlight here. Passion, purpose, and people. Man, clap it up for Avery. Excellent, excellent job. And clap it up for yourselves. You all did a great job. These are some of the best bridges we've ever seen. I still see some of my favorite schools are hanging in it with us. I see Corinth, St. Joseph, Waltrip, All Hallows, St. Peter. Shout out to you all. Scallon, Ursuline, the Scholars Academy. Excellent job today. Well, we want to highlight though, hey, this isn't the last day that we want to spend some time with you engineering tomorrow. We got plenty of labs. We have plenty of special events coming up. We have plenty of labs for you to get involved with. And please don't forget, most importantly, you know, fill out the exit ticket. And if you have some cool videos and images, you know, show them on social media and you'll point directly hashtag, you know, engineering tomorrow. Give us a shout out as well. So let me hand it over to my good buddy, Monica, to talk about next steps. What's next, Monica?
Well, next is exactly what you said.